Let's take a closer look at some of the things we've defined so far and see how they relate to one another. Firstly, we have force, which is defined as K Q1 Q2 by R squared. We have electric field, which is equal to KQ by R squared. We have potential energy, which is KQ1 Q2 by R. And we have voltage, or electric potential, which is KQ by R. If we are to relate these quantities, we can start with force and realize that when we multiply by distance, we obtain the potential energy, right? So that's going from this one to that one. And for both of these, we can divide by charge of the other particle, right? To determine for force it becomes the electric field, and for potential energy it becomes voltage. And so now obviously if I multiply the electric field by distance, I get voltage. So this gives us a set of equations that we can use to relate these quantities. Firstly, F is equal to U by R, and accordingly E is equal to V by R. These are more commonly expressed as U equals FD and V equals ED. And then we have F by Q equals E and U by Q equals V. These are also commonly expressed as F equals QE and U equals QV. Now, there does exist a caveat with these two equations and how they kind of relate with one another, which is that in some cases you may see it written as U equals minus FD and V equals minus ED. This is just a sign convention, and what it primarily has to relate with is how the energy flows in and out of a system. So oftentimes it's best to just kind of go with these equations as a basis. And if you have an understanding of energy flow, then try and consider how they flow between systems and in which case one is used. And try and intuit it, what makes more sense. I'll provide some examples using these problems so we can see when to use what. Now, some more differences to note is that the force and the electric field are vector fields, whereas potential energy and voltage are scalar fields. What does this mean? Well, if I have my plane of space, then I can consider at some point the electric field, which will look like an arrow. This arrow is called a vector, hence why these are vector fields. The force vector will exist only if I have some particle that has a force exerted on it, but it will also be an arrow indicative of the magnitude of the force and the direction of the force. In contrast, the voltage at a point will just be a number. It will not have any direction associated with it. And the potential energy between 2 points, so I will need another point here, there will be a scalar quantity. It will just be a number relating between the 2 points what is the energy of the system. Now I want to clarify some things about the definition of potential energy and voltage. When I have two particles, Q1 and Q2, separated by a distance r, I can calculate the potential energy using my formula U equals K Q1 Q2 by R. But if we want to be even more clear about what this statement is really saying, it is saying that if my particle Q2 happens to be a distance infinity away from Q1, and I then brought it from infinity to this distance r away from Q1, the work, or the amount of energy necessary to make that happen, is given by this equation. This is the amount of energy it takes to bring Q2 from infinity to r. Or equivalently, you may say, to bring Q1 from infinity to r, away from Q2. Now the reason this is important is because if I have some problem that involves two particles and it asks how much energy does it take to move this particle from here to here, then you can very easily find that by determining the potential energy of the system here between these two and the potential energy of the system between these two and finding their difference. But if you get some problem that states how much energy will be required to bring this particle from infinity to some distance r, then you will need to know this more inherent definition of potential energy in order to realize what the value will be. Equivalently, you can say that the potential energy of the system at r equals infinity is 0. And you can also kind of see that from the equation. Now, analogously, voltage has a similar concept where if I have some particle q, the voltage at some distance r is assuming that if r were infinity, then the voltage at that infinite point would be 0. Also pretty straightforward from the definition. If I am to calculate the voltage difference between two distances, r1 and r2, then I can calculate the voltage at r1 and the voltage at r2 and find the difference, however they ask for it. And of course, for all four of these quantities, you can determine when I have many, many more particles what the force or electric field or potential energy or voltage is by summing over different forces or electric fields or potential energies or voltages. So if I have, for instance, 3 particles, I can determine the force on this particle by summing the force due to particle 1 and the force due to particle 2. And I can find the electric field at some point here by summing the electric field due to this point and the electric field due to that point and the electric field due to this point. And I can find the potential energy of all 3 of these particles by summing, if we call this 1, 2, 3, the potential energy between 1 and 2, the potential energy between 2 and 3, and the potential energy between 3 and 1. And I can find the voltage at this point by determining the voltage by 1 plus the voltage by 2 plus the voltage by 3. So all 4 of these quantities may be easily extended to higher quantities of particles.